Welcome to this tutorial on rate splitting multiple access for beyond 5G, principles, recent advances, and future research trends. My name is Bruno Clerks. I'm a professor of wireless communication and signal processing at Imperial College London. And this tutorial is given jointly with my colleague, Dr. Yiji Lina Mao. This tutorial will be divided into two parts. The first part will be given by myself, and part two will be given by Lina. So in the first part, I will first introduce the notion of multiple access, and in general, rate splitting multiple access. We will then look into the motivation for a new physical layer. I will give two major motivations to design a new physical layer. And in the third subpart here, we will look at rate splitting multiple access into more details. And in part two, Lina will first look at precoder optimization and physical layer design of rate splitting multiple access. And then part 5 or subpart 5 will be dedicated to application of RSMA to numerous scenarios that we will envision in beyond 5G. And finally, in section 6, Lina will conclude, look at future challenges and pathway to 6G. So in these introductions, we will first look at Mimo networks, have a very brief overview of what Mimo networks are and existing multiple access techniques. Point-to-point Mimo is well understood for a long time. Let's consider here a scenarios where we have a transmitter equipped with M transmit antennas, and we have a receiver here equipped with N receive antennas. And we have a Mimo channel H that has dimension N by M. And so MISO, SIMO, and SISO actually particular instances of a Mimo case. MISO refers to the case where we have single receive antenna, SIMO to the case where we have single transmit antenna, and SISO to the case we have single transmitted receive antenna. And for the general Mimo channels, the ergodic capacity is known for over 2 decades and is given by this relationship here, which tells us essentially that as the SNR increases and grows large, this capacity can be expressed very simply as the minimum between the number of transmit antennas multiplied by the SNR in dB plus a term here that doesn't scale as fast as log2p. So this term here scales slowly compared to log2p. So this is an approximation of the capacity in the high SNR regime. And the important message that we want to show here is that the pre-log factor of this capacity, so this term here, is equal to the minimum between the number of transmit and receive antennas. This pre-log factor is what is called multiplexing gain, or also called degrees of freedom. And it tells us the slope, essentially the slope of the capacity versus SNR in dB in the high SNR regime. And so this DOF here, or this multiplexing gain, is given by the minimum between the number of transmit and receive antenna. As we increase this minimum, essentially the slope of the rate or the slope of the capacity versus SNR increases. And so if we increase the DOF, the rate will increase faster with the SNR in the high SNR regime. So this can be, DOF can be interpreted in terms of slope of the rate of the achievable rate versus SNR. It can also be interpreted as the number of interference-free streams that can be transmitted in parallel. So here in these point-to-point Mimo channels, we can transmit a number of interference-free streams that is equal to the minimum between the number of transmit and receive antennas. Now, what is interesting is that this DOF given by this, is resilient to CSIT inaccuracy. So even if we don't know the channel state information of the transmitter accurately, so CSIT stands for channel state information of the transmitter, even if this CSIT is not perfect, we can still achieve degrees of freedom that is equal to the minimum between M and N. That's a very important point when we have point-to-point MIMO channels, and we will see that actually this is not the case when we have multi-user scenario. Right, so nowadays networks, they are not limited to single users, they are inherently multi-users, and so the question is, how do we deal with multiple users? So assuming here we have K users. And what is the benefit of multi-antenna in these multi-user settings? So to look at this, we can look at two different setups. We have the broadcast channels and we have the multiple access channels. So the broadcast channels is a complicated terminology to refer to the downlink of a modern communication system. And the multiple access channels refers to the uplink. And so in the downlink, essentially we have one transmitter that wants to serve multiple users using multiple antennas in general. And those users are served in the same, potentially same time frequency resource. In the uplink, multiple users transmit at the same time on the same time and frequency resource. And there is one receiver that captures all those received signals and processes them. So in this tutorial, what we're going to look at is the downlink. So we're going to focus our attentions on this scenario here. Right, so let's look at this downlink multi-user scenario. So again, this broadcast channel, we have a transmitter that wants to send independent streams to multiple receivers. So here we have a transmitter that is equipped with multiple transmit antennas, M antennas, and we have K users, K receivers here. In this example here, K single antenna receivers, K single antenna users. We have K vectors here that represent the channel state information of those K users, so H1 to HK. And we can show that if we know those channel state information perfectly at the transmitter, so if we have perfect CSIT, the optimum sum multiplexing gain is given by the minimum between the number of transmit antennas and the number of users. Again, this is a well-established result for almost 20 years. Right, so this is in terms of sum multiplexing gain. So what does that mean? That means actually the sum rate of this system here will scale, the pre-log factor of the sum rate will be given by this quantity at in the high SNR regime. And we'll come back to this in more details later on. Right, so if we have a SISO BC, so M is equal to 1, then in that case, the minimum between 1 and K will be equal to 1. So we have a DOF of 1. That means that we can transmit only one interference-free stream in this network. So the sum rate will scale as log 2P, essentially. And to achieve the capacity of the SISO BC, well, the strategy is known, the capacity region is known, and the capacity achieving strategies are known. There are two of them. The first one is superposition coding with successive interference cancellation. And the second one is called dirty paper coding. And we'll come back to those techniques a bit later on, especially the first one. Now, if we have multiple antennas at the transmitter, so that's the MISO case, MISO BC, multiple transmit antenna at the transmitter and single antenna at the receiver, or if we have the MIMO BC case, so multiple antennas at all nodes, then the strategy of superposition coding with SIC is clearly suboptimal. And the reason for this is that users cannot be ordered because we deal with vector channels or matrices. And that contrasts with the single antenna case where we had only scalars. So in the single antenna case, the SISO BCs users could be ordered according to their channel strength, and that enables us to use superposition coding with SIC. When we have multiple antenna setup, users cannot be ordered anymore. And so that's the reason why SCSIC is suboptimal and leads to a performance loss. Now, this SCSIC is the basic building block of what is called non-orthogonal multiple access that we will describe in a minute. So what we are left with in terms of capacity achieving strategy is dirty paper coding. So dirty paper coding is capacity achieving when we have multi-antenna broadcast channels. So in this scenario here, with multiple antennas at the transmitter, the only known capacity achieving strategy is DPC. This is in the case where we have perfect channel state information at the transmitter. Right, so moving on to another form of multi-antenna processing. Now when we have multiple, so here instead of having only one transmitter serving multiple users in one cell, we could have a multi-cell scenario like here, where we have multiple cells, a base station in each of those cells, and each cell serve multiple users. And so the problem in multi-cell MIMO is that we can coordinate or enable some form of cooperation among all those base stations, such that we jointly allocate resources across the whole network in order to manage the interference across the network and to boost the rate performance of all those users. So there are typically two types of schemes: coordination, that only share the CSI, the channel state information, among the base stations, and cooperation that share the CSI plus the data. And that enables us to do two forms of schemes. On the left side, coordination, we have CS is coordinate scheduling, CB coordinate beamforming, PC power control. So here we manage the interference among all those cells by just trying to reduce the interference level that, for instance, this transmitter would create to that users here by leveraging the presence or the availability of the CSI that has been shared among those different base stations. On the other hand, cooperation, well, here what we do is that we share the data and the CSI so that all those antennas at all those base stations act as a giant antenna array and can perform joint transmission of data across all those different users. Right. The baseline is that for those two schemes, again, it's very important to know the channels at the transmitter in order to enable these coordinations among the different cells or this cooperation. Right. Another form of MIMO processing is massive MIMO. So there we take the scenarios that we had earlier on with one cell. So this, and we scale the number of antennas, typically at the base station. So here what we do is that we really try to leverage the very large number of antennas at the base station. And so in a downlink case, it would be a very large number of transmit antennas. And this large number enables us to create very sharp beams, narrow beams, also called pencil beams or laser beams, so very sharp beams. And those sharp beams reduce the multi-user interference. And so the benefit of massive MIMO is that you can actually rely on relatively simple precoding techniques, relatively simple processing at the base station to serve quite many users on the same resource blocks. And so that also helps to simplify the scheduling. The drawback is that as we increase the number of antennas, there is a need for an accurate channel state information at the transmitter. And this is can be a challenge because we can have pilot contamination problems that actually will lead to a degradation of the quality of the channel that is actually acquired at the transmitter, at the base station. We could have also CSI exchange overhead. Another drawback is the impairment due to hardware. Aside channel estimation error, we have RF impairments for instance, phase noise that will lead to actually also inaccurate estimate of the channel. And we can have relatively high costs in terms of power consumptions, hardware and computational costs because of the large number of antennas. Right, so let's now look at different type of multiple access techniques that have been in the literature and used over the past decades. So the most well-known one is OMA, that stands for orthogonal multiple access. Then we have SDMA, spatial division multiple access. And then we have NOMA, that is non-orthogonal multiple access. And here they're actually on a line that goes on one side from orthogonality to the other side is non-orthogonality. So what does that mean to have orthogonal multiple access? It means actually we allocate users into orthogonal resources. And orthogonal means that they will not create any interference. So for instance, in a time division multiple access, we allocate users across different time instances. So we schedule one user at the first time slot, another user at the second time slot, the third one at the third time slot, and so on. In the frequency domain, so frequency division multiple access, we use the frequency domain to separate the users. So we have one user at the first frequency, another user in the second frequency, and the third one, and so on. So they use orthogonal resources in time or frequency, and that by doing so, we make sure that we don't have interference between different users. Another domain that we can exploit is the code domain, code division multiple access. So here, each user is allocated different code, orthogonal codes, that's such that the users are separated in the code domain. And now finally, we have OFDMA, so based on orthogonal frequency division multiple access, which split time and frequency resource into blocks, right? You can say resource blocks like this here. And we allocate each resource, each block to one user at a time. Right, so the bottom line among those four here, those four methods, they use different domain, but essentially they eliminate the multi-user interference. Now, there is another domain that we can exploit that we don't have here on this slide, which is the spatial domain. And this relates to this notion of space division multiple access. So here we multiplex users in the spatial domain using multi-user linear precoding. So we use the spatial domain, so multiple antennas, to separate users. And this is heavily used in multi-user MIMO, in network MIMO, in millimeter wave MIMO, in massive MIMO. So all the processing that I mentioned earlier on here in massive MIMO, in multi-cell, in downlink multi-user broadcast channels relate to space division multiple access. So here we use those multiple antennas at the transmitter to manage the multi-user interference by creating beams that hopefully will not create interference among each other, and by treating any residual interference at the receiver as noise. Right. Now, this is relatively important in the sense that the interference that we create by scheduling multiple users on the same time and frequency resource, but on different beams, this interference may not be zero. Each user here, user 3, may still see some interference from the data that is actually transmitted to user 2 and user 1. And this really depends, the amount of interference really depends on what type of processing we do at the base station here and the quality of the channel state information that we have available at the transmitter, right? So SDMA, in a way, is not a form of orthogonal multiple access. It's more a form of actually non-orthogonal multiple access because the interference is not necessarily equal to 0, right? So that's an important point to keep in mind. Now, non-orthogonal multiple access is relies on this notion of superposition coding with successive interference cancellation that I mentioned earlier on. And it uses the power domain to break the orthogonality. So what we do here, we transmit multiple users on the same time and frequency resource. We don't separate them in the spatial domain like in SDMA, but we separate them in the power domain using superposition coding at the transmitter and successive interference cancellation at the receiver. So the way it works here is that, let's imagine we have a transmitter with one antenna and we have two users, two single antenna receivers. The base station will actually superimpose in the power domain the message of user 1 and the message of user 2. So on the same time and frequency resource, we transmit two messages that are superimposed in the power domain. And at the receiver, what will happen is the following. User 1, let's say user 1 is a strong user, he has a good channel compared to user 2. User 1 will decode the message of user 2. User 1 will decode the message of user 2, will perform successive interference cancellation. So we'll decode the message of user 2, will cancel it from the message of user 1, right? So of user 2 will remove the red part and then will decode his own message. The user 2, on the other hand, is the weaker user here. He's maybe further away from the base station. He has a weaker channel strength. What he will do, he will treat the message of user 1 as interference. So he will see the interference from user 1. He will treat that interference as noise, and he will decode his own message in the presence of the interference of user 1. So the important message here is that we see the way the interference is managed is by trying to decode the interference at the receiver. User 1 here is trying to fully decode the interference that is created by the message intended to user 2. So it has a receiver based on successive interference cancellation that fully decode the interference of user 2. But this is a completely different architecture from what we have in SDMA, where in SDMA, the receivers are very simple. They just treat interference as noise. They don't have to cancel any form of interference here at the receiver, right? But here, the receiver has to be equipped with SIC in order to cancel this interference. Right, so those are actually the difference between OMA, SDMA, and NOMA. And we'll come back to this notion of fully treat interference as noise versus fully decode interference. Right, so now we may wonder, but if we do NOMA in here, well, why not having multiple antennas at the transmitters and potentially at the receivers as well, right? So we can do that, and this is often referred to MISO NOMA or Mimo NOMA, and this is an example here, where we have, for instance, multiple antenna base stations. We have multiple groups of users here, group 1 all the way to group G, and in each group, we have multiple users. And so the way we operate is that we use multiple beams to separate those groups, right? So we try to separate them in the spatial domain, and in each group, one of the user will be considered as a strong user and will decode the interference or the message coming or intended to the other users. For instance, user 1 here in this group will decode the message of all those other users in this group 1. So he will use SIC to decode those messages of user 2 all the way to user G, cancel it from his received signals before decoding his own message. Now, what we'll see later on that we have to be very careful with doing that, because we can show that doing multiple antenna NOMA leads to an inefficient use of the multi-antenna dimensions, and in particular, these multiplexing gains or degrees of freedom that I talked about earlier on is actually decreased significantly when we perform NOMA in a multi-antenna setup. So it leads to a loss in terms of multiplexing gain or degrees of freedom and therefore rate, and also it leads to an inefficient use of successive interference cancellation receiver at the receiver, and I will show you this later on. For more information, you can refer to this reference. Right, so let's now move on to a motivation for a new physical layer. And I will give you two motivations. The first motivation is the problem of imperfect channel state information in the transmitter. The second motivation is based on the limitation of the existing multiple access techniques. So let's start with the first one. So let's take again our pictures that we had earlier on with a transmitter, multiple antennas, and we have K single antenna receivers. And I said earlier on that we have K channel vectors here. And so the transmitter has to know those channels at the transmitter. It has to know them in order to perform efficient interference management and processing. And so the way this is done is by having channel estimation and feedback or channel acquisition in general of those K channels at the transmitter. And so the estimate of the channels of user 1 here is, for instance, denoted as H1 hat. So the transmitter does not know H1, but knows H1 hat. It knows it has an estimate of the channels of user 1. And same for all the other channels, right? So in general, the true channels is H1 to HK. What is known at the transmitter is an estimate of those channels, H1 hat to HK hat. And why H1 is different from H1 hat or HK different from HK hat is because we have many impairments when we perform channel acquisition. We could have quantization error. For instance, if we have limited feedback-based or codebook-based feedback, we have quantization error. This can happen if we use this in FDD, but also if we use it in TDD. This is a classical problem in 4G and 5G. We have channel estimation errors, just simply because of the estimation errors, the noise that we have when we perform estimation. We have delay in mobility. So we have this estimation. This estimate is maybe done every 5 milliseconds or 10 milliseconds, but then between the time we perform channel estimation or channel acquisition and the time we use those estimates, there may be a latency there. And in the meantime, the mobile or the users may have moved. So the channels may have moved in between. So if we have just a few milliseconds delay and we have mobility at 3, 10, 30 kilometers per hour, we're going to end up having essentially an inaccurate channel estimate at the transmitter. And then we can have channel acquisition that is done not on each frequencies, on each subcarriers where we have OFDMA, but can be done at the resource block level, at the subband level, and we could have a bit of frequency selectivity within this subband. That's also possible. And finally, we can have hardware impairment, phase noise, RF impairment in the form of additive multiplicative noise. We can have miscalibration of the RF chains. All those impairments will lead to an inaccurate channel estimate at the transmitter. Right. So if we take our conventional architecture that is used in 4G and 5G that relies on typical multi-user MIMO processing or SDMA, we have what is called multi-user linear precoding. And the way this works is the following. We have K users that we want to schedule, and each user wants to receive a message. So a message W1 intended to user 1, WK to user K, WK capital K to user capital K. So those K messages are encoded into K stream S1 to SK. They are then linearly precoded. They are transmitted over those M transmit antennas. They are broadcasted over the air, and then each receiver will try to decode his own streams. So user 1 will try to get an estimate of W1, the message of W1, and by doing so, will treat any residual interference that he sees from the other streams as noise. Right, so how does our transmit signal vector look like at here after linear precoding is as follows. We have a weighted, a sum essentially of k stream S1 to Sk, and each sum is multiplied by a vector here, which is the precoder for a stream 1 and all the way to stream k. And those precoders, those k vectors, they are designed based on the available channel state information at the transmitter. And so if it's imperfect, we have an estimate of h here. We have an estimate of those k channel vectors. Then our precoder has to be designed here based on this estimated channel. Right, so let's look at the case where our channel state information transmitter is perfect. So in that case, our H estimate, H hat, is equal to the true channel, and things are simpler. So what we can do, assuming that we have more antennas than the number of users, we can do simple zero forcing precoding. And so this is the expression of a zero forcing precoding. Essentially, it forces any interference to 0. So in other words, here, if I look at here, I will design the precoder of stream 1 here of S1, P1, such that P1 will not create any interference to user 2, user 3, user 4, all the way to user k. So we force any interference to 0. And this is something we can do because we have perfect knowledge of the channels at the transmitter. And so if we can get rid of all the multi-user interference, it means actually each receiver K will be given by an intended term here that will be a function of the transmitted stream of user K and the noise at user K. We don't see any multi-user interference simply because the multi-user interference was forced forced to 0 thanks to this zero forcing precoding. So this is very nice because that means actually each user K will receive one interference-free stream. User K here will receive Sk without seeing any interference from the other streams that are transmitted in parallel. And so we get a sum DOF of K. We can transmit K interference-free streams in this network. We can transmit in parallel K interference streams that do not interfere with each other. Right. And so obviously, what we want to do is to have this DOF as large as possible. So if we have M larger than K, I mentioned earlier on that the DOF is the minimum between M and K here. So this is really the case. If M is larger than K, the minimum is equal to K. And so indeed, we can transmit M interference-free streams in the network. Right. So this is a well understood case. And so how does that translate in terms of rate? Well, if I have here the rate, let's say, for instance, the sum rate versus SNR, and if I have K equal to 2, M equal to 2, K equal to 2 and M equal to 2, I can achieve a certain degrees of freedom, right? A certain multiplexing gain. If I can increase the number of users and the number of antennas, I can actually increase the multiplexing gain, right? So we see here that we have red and blue here. The large dimension, having more users and more antennas, leads to a larger DOF than having fewer antennas. Right. So we have the sum rate, the pre-lock factor of the sum rate is actually the sum DOF is being increased. Right. Now, something to mention as well, and is that in general, we want to increase this DOF. We want to increase it as much as possible because the DOF refers to the slope here of this sum rate. And so if the DOF is higher, that means actually the sum rate will increase faster with the SNR. And so in this example here, this does not relate directly to this DOFK, but what we want to show here is that if you have two different strategies that actually operate on the same number of users and the same number of antennas, you would always prefer to have a strategy that has a higher DOF because its sum rate will increase faster with the SNR. So in this case, between the red and the blue, a red strategy would be better than the blue strategy. And here for 4 antennas and 4 users, the same. Right, so now what happens if we have imperfect CSIT? If we have imperfect CSIT, then H hat is different than H. And so in that case, the channel at user K is given by an estimate plus some error. And what is known at the transmitter is not HK, it's HK hat, is the estimate of the channel of user K. And what we're going to do here is to model the error, this error here. We're going to model it relatively simply by saying this error, the power of this term essentially scales with P, scales with the SNR, with a certain exponent alpha. And this alpha is larger than 0. So it's positive. It's larger or equal to 0. So that means actually we have the error, the power of the error terms will decrease with the SNR. So let's take alpha is equal to 1. For instance, we have this is 1 over P. So essentially, as P increases, the variance of the error will decrease with the SNR. Right? That makes sense. As you have higher SNR, you have less error, maybe estimation error, for instance, and so your error variance decreases. The alpha tells us how quickly it decreases with the SNR. So if you have alpha is large, it means actually this error variance will decrease more quickly with the SNR. And so the alpha will be taken between 0 and infinity. And one way to interpret that is in terms of feedback bits. So for instance, if we have alpha equal to 0, it means actually the power of these terms is constant, whatever the SNR. And this is something we obtain when we have a CSI acquisition mechanism at the transmitter that is based on limited feedback or codebook-based feedback, and the number of bits of feedback is fixed. This is typically what we have in 4G and 5G. If alpha is increasing, it means that actually we increase the number of bits of feedback as the SNR increase. And if alpha is equal to infinity, essentially we have an infinite bit of feedback. It is equivalent to having perfect CSIT. Now, if alpha is equal to 1, we can show that from a degrees of freedom perspective, this is equivalent to having perfect CSIT. So that's why in the sequel, what we're going to do is that we're going to focus on alpha between 0 and 1. And by doing so, we can operate in the wide range of situations where we have a very poor CSIT quality all the way to having something that is actually equivalent to perfect CSIT from a DOF perspective. Right, so what is the effect of having imperfect CSIT? Well, that means actually now we cannot do, if we do zero forcing beamforming, we have to do it based on the channel estimate. And the problem is that we have interference left here. So compare with what we had here, where we had no interference in the system because we couldn't force the interference to 0. Now we have interference left into this network that is marked here into red. So when I decode, when I have my receive observation for user K, I have the intended signals for user K, SK, but this is corrupted by the message that, or the stream that actually transmitted to the other users. And what we can show is that now the degrees of freedom, the sum degrees of freedom, so the pre-log factor of the sum rate is not equal to K anymore, is equal to K alpha. So if alpha is between 0 and 1, essentially the sum DOF is decreased. So the slope of the sum rate versus the SNR is decreased. And this is what we see in this figure here. If you have alpha equal to 0, you see that the DOF is equal to 0. So that means that at high SNR, essentially the slope of the sum rate versus SNR will be equal to 0. If alpha increases, then the slope increases all the way to when alpha is equal to 1. And so in this regime here, between alpha equal to 0 and alpha equal to 1, we see that the slope is increasing as alpha is increasing. And that means that our sum rate will also increase faster as alpha is increasing. But we see that we can have a wide range of performance depending on the CSIT quality, depending on alpha. Beyond alpha equal to 1, we see that the slope does not change between alpha equal to 1 and alpha equal to 10. The slope does not change. And the reason for this is because any alpha larger than 1 leads to a perfect CSIT from a DOF perspective. So alpha larger than 1 does not increase the multiplexing gain, the sum multiplexing gain. Right, so let me show you an example here of alpha equal to 0 that is based on realistic codebook-based feedback. And so here we have sum rate versus SNR, and we have different codebook design for the feedback. But the main message here is see what's happening as a function of the number of bits. So we have 2 bits, 3 bits, 4 bits for those 3 blue curves. And the black curves is when we have perfect CSIT. So we see there is a big gap between the black curves and the blue curves. And the performance here of the blue curve saturates. You see it's getting flat here. So if it's flat, it means that the slope is equal to 0. And so we have essentially a DOF of 0. And this is really what you have in 4G. And you can have this in 5G as well, because the number of feedback bits is fixed with the SNR. So at high SNR, essentially the sum rate will saturate. And so by increasing the number of bits, we see that this plateau here actually is shifted upwards, but nevertheless, we still have a saturation. Right, and so why is this happening? Well, this is happening because we enter here a regime where the multi-user interference coming from this term here is not negligible compared to the noise. And because of that, the SINR is actually limited by the multi-user interference. And so treating multi-user interference as noise leads to a significant performance loss. And this is what we see here. Right, so if we take some distance with respect to what the community has done in the past 2 decades, is we can draw the following observation. The conventional approach here relies on the following. We start with an information theoretic channel, for instance, the multi-antenna broadcast channel. We try to characterize the information theoretic limit, so the capacity region. And we do this by assuming perfect CSIT. Then we identify that the capacity achieving schemes under perfect CSIT is dirty paper coding. Then we realize that dirty paper coding is actually very complex to implement. So it's better to, it's more realistic to use some form of linear precoding. And so we bring it signal processing and optimization tools to design those precoders. And at the end, we realize actually the CSI is not perfectly known at the transmitter. So we actually bring in robust optimization tools to robustify the precoder design. But the baseline is that at the end, the system model that we play with is always this multi-user linear precoding. X is equal to a sum over the k users of pk multiplied to sk. But we have to keep in mind that to obtain this, the starting point was perfect CSIT. So we assume we had perfect CSIT here at the very beginning. So this system model here is in a way motivated by having perfect CSIT from the very beginning. Now, what has been done in the past few years is to bring the notion of imperfect CSIT at the very beginning. So looking at information theoretic channels of multi-antenna broadcast channels with imperfect CSIT. And this remains an open problem in information theory. So the capacity region here is unknown. And so instead of looking at capacity region, people have looked at degrees of freedom region, degrees of freedom of multiplexing gain in order to try to find an approximation to the capacity. And now what we know is that we have identified the optimal degrees of freedom region when we have imperfect CSIT in multi-antenna BC. And it turns out that the optimal schemes to achieve these optimal degrees of freedom is based on rate splitting. And so once we have this rate splitting architecture, then we can bring it signal processing and optimization to optimize this communication strategy. But what we obtain at the end is a communication scheme based on rate splitting that is not the same as what we had here. It is given by a term here on the right side that is reminiscent to what we had here, but we have additionally here, we have an additional stream that is transmitted, SC multiplied by PC. And this presence of this stream here is motivated by the optimality from a DOF perspective in the presence of imperfect CSIT. So from a DOF perspective, if the CSI becomes good enough, if it becomes perfect, essentially, this common stream, what we're going to call common stream in a minute, this streams actually does not enhance the performance from a degrees of freedom perspective, and the scheme boils down to what we have been using before. Right. So just to step back a little bit again, so if we think about imperfect CSIT, this is a more general problem than the perfect CSIT. Perfect CSIT is a particular case of imperfect CSIT when the channel estimation error is equal to 0. So that makes sense that if we deal with a more general problem, we have to actually come up with a more general class of communication strategy. And this is what rate splitting offers, is a very general class of communication strategies that can boil down to the existing communication strategies that we have been looking at so far in the case where we have perfect CSIT. So for instance, here, if we turn off this stream here, we end up with a system model that actually is reminiscent of what we had earlier on. And what we're going to look at in this tutorial is two strategies, dirty paper coded rate splitting and linearly pre-coded rate splitting, that actually are kind of a more general class of strategies where DPC and classical linear pre-coding actually subset of this general class, right? So we'll see the first motivation is essentially to tackle this imperfect CSIT problem, and to do this, the rate splitting is an enabler of a more general class of communication strategies that tackle the general case of imperfect channel state information at the transmitter. Now, the second motivation is due to the limitation of existing multiple access schemes. So SDMA, that I talked about quite a bit already, is quite good in the sense that it enables us to obtain the full DOF, spatial multiplexing gain, when we have perfect CSIT, so some DOF. So I mentioned the minimum between M and K before. This can be achieved by space diffusion multiple access when we have perfect CSIT. And it does this with a very low precoder and receiver complexity. The drawback is that it really works well when the number of antennas is larger than the number of users. If the number of antennas is smaller than the number of users to be served, then it is not very efficient to manage the multi-user interference. The second drawback is that it works well when the users are relatively orthogonal to each other. So when the channel directions are relatively orthogonal to each other and have a similar channel strength. More general settings where they don't have similar channel strength, or if they're not orthogonal, then there is some performance degradation. And the third drawback is this, though it's optimal when we have perfect CSIT, it's actually suboptimal when we have imperfect CSIT. And so again, to re-emphasize, the main property of SDMA is to really fully treat any residual interference as noise at the receiver and move all the processing at the transmitter. Right, NOMA, on the other hand, the advantage is actually we know it's a good strategy when we have single antenna nodes. So the size of BC, it's actually capacity achieving. And it works really well when we have a diversity of user channel strength. The drawback is that this SCSIC is motivated by single antenna. It's not motivated by multi-antenna broadcast channels. The second drawback is that it's suited to aligned users with diverse channel strength. Does not work in general with non-aligned users and diversity and maybe channel strength that are not sufficiently diverse. It's very complex at the transmitter and the receiver because the precoders now have to be optimized, but this is quite common with all the schemes, but along with the groups and the decoding orders. So here in this figure here, the groups have to be optimized and who decodes what has to be optimized as well, which leads to quite significant complexity. And at the receiver, it has significant complexity at the receiver because we need multiple layers of successive interference cancellations, which SDMA did not have because it just treated interference as noise. And the fourth drawback is actually it leads to a DOF loss. And in DOF loss in both perfect CSIT and imperfect CSIT. And that comes from the fact that it exploits the multi-antenna inefficiently, and it exploits the presence of the SIC inefficiently. Now, the property, as I mentioned earlier on, the key to NOMA in the scheme design is to fully decode and cancel the interference created by the other users. But this is a complete opposite to what SDMA is doing, that was treating interference as noise. Right, so what rate splitting will do here, in this context of multiple access, it will be an enabler of a general and flexible multiple access framework that we call rate splitting multiple access. And we will show that SDMA, OMA, NOMA, and multicasting are actually particular instances of a general multiple access framework that is called rate splitting multiple access. And this rate splitting multiple access enables you to bridge SDMA and NOMA, SDMA that fully treat interference as noise, NOMA that fully decode and cancel interference. RSMA will enable to softly bridge those two extremes by partially decoding interference and partially treating interference as noise. And by adjusting how much interference we decode and how much interference we treat as noise, we can evolve between SDMA and NOMA, and consequently have a performance or rate performance that is always either equal or better than both SDMA and NOMA. Right, so let's now look at into more details at rate splitting multiple access. So now we'll look at the architecture of RSMA, and we'll look at the degrees of freedom and the rate enhancement offered by RSMA. So let me show you two user examples that you can understand using this basic toy example, how it works. So let's imagine I have two users to schedule, and I want to transmit to two users. I want to transmit two messages, W1 to user 1, W2 to user 2. So we have here at the receiver, we have two users, user 1 and user 2. And this is the architecture of user 1 receiver. User 2 has the same architecture, exactly the same thing. Some of those parameters are different, but it's the same architecture. It's based on successive interference cancellation. And here we have the transmitter. Right. So what do we do at the transmitter? We split the messages. That's the first part that is completely new to the rate splitting, is that we split the messages. So what does that mean? We have a W1 here, and we split it into two parts, WC1, WP1. WC1 that goes here, WP1 here. So this we're going to call the common part. This is what we're going to call the private part. And we do the same for W2. We split into two parts. So that means that we take the bits of W1, and some of the bits goes into WC1, some of the bits goes into WP1, and similarly for W2. And then we create a common message by taking WC1 and WC2. We take them together and we combine them into WC. And so here, from those four parts here, we take those two and we combine them into WC. And then we do encoding. So we do independent encoding of those three messages here. WC is encoded into a stream SC, WP1 into S1, WP2 into S2. SC will be called a common stream, S1 is called a private stream for user 1, and S2 is the private stream of user 2. So we see that information for user 1 is encoded into S1, but is also encoded into SC, right? Information for user 1, part of it will go into SC, part of it will go into S1. Information for user 2, part of it goes into S2 and part of it goes into SC. And then we linearly precode those three streams. And so we have PCSC, P1S1, P2S2. So from two messages here, we now have created three streams. From two messages, we have created three streams. What do we do at the receiver? Now, SC carries potentially information that is of interest to both user 1 and user 2, because user 1 wants to retrieve WC1 and user 2 wants to retrieve WC2. So both users, user 1 and user 2, will have to decode SC, and they do this by treating S1 and S2 as nodes. So they will decode both users here. I take for user 1, for instance, user 1 will decode SC into WC prime, but WC hat. So it will retrieve the common message here. From there, it will retrieve from WC, it will retrieve the part that actually is intended to user 1. So it will retrieve WC1 from WC, and hopefully WC1 hat here will be the same as the one here. And then it will perform SIC, so it will re-encode WC, perform successive interference cancellation, and then will actually decode S1, the other stream that is intended to himself, to user 1, and retrieve WP1, the private parts. And from WC1 and WP1, it will recombine those two parts into the original message, and hopefully W1 hat will be the same as W1 there. So what we do at the receiver is that both users decode the common stream first by treating S1 and S2 as noise, and then both users will perform SIC, and user 1 will decode S1, user 2 will decode S2. Now, what is the rate of user K? And this is why it's called rate splitting. The rate of user K is the sum of two rates. The rate of user K is the rate of the private stream of user K, SK, plus part of the rate of the common stream. The rate of user 1 is equal to the rate of S1 plus part of the rate of SC, because SC carries part of the message of user 1. So that's why we have two parts in the rate. The rate has been split into two parts. We have the rate of the private part and part of the rate of the common streams. So where is SDMA and NORMA in that scheme? Well, let's look at that. If I want to look at SDMA based on multi-user linear precoding, the only thing I have to do is to turn off the common stream. So I simply allocate 0 power to the common stream. By doing so, nothing goes into this stream here. W1 is not splitted and it goes directly into S1. W2 goes directly into S2. And so W1 is encoded into S1, W2 into S2, and what we have is P1S1 plus P2S2. We don't have the common stream here. That common stream is gone. What about NORMA? Remember that in NORMA, we have one user decode the message of the other users. So here, how can I obtain NORMA from this? Is the following. I allocate, for instance, let's assume user 2 is the weaker user. I allocate 0 power to the private stream of user 2. So here, S2 here is equal to 0. And I'm left with only two streams, SC and S1. I encode W1 into S1, and I encode W2 into SC. I encode W1 into S1, I encode W2 into SC. What does that mean? That means that because W2 has been encoded into the common stream SC, both users will now decode W2. User 2 will decode W2, but user 1 also will decode the common stream, and so will decode W2. And so in NOMA, user 1 will decode the common stream, will decode W2, will perform SIC, and then will decode his private stream S1. And user 2 simply will decode the common stream and then does not have anything anymore into the private streams S2, so it does not have to go into the next step to decode S2 because there is nothing there. Right, so what is the transmit signal? Well, it's now PCSC plus P1S1. I have here transmitted W1 into S1, and here in SC, I have transmitted W2. Right? So what we see here is that we have two different multiple access, SDMA and NOMA. Actually, those two are two subsets of RSMA, and they are obtained differently. MULP is obtained by turning off the common stream, and NOMA here is obtained by turning off some of the private streams and encoding one of the message directly into a common stream. So NOMA has a common stream, is usually not called common stream, but has a common stream. And this common stream is simply a message that is decoded by all the users, but it's not necessarily intended for all the users. For instance, in NOMA here, SC is decoded by both the users, by both user 1 and user 2, but is not intended to user 1. It's only intended to user 2, right? So this is a common stream, and is, in a way, we have this, more generally speaking, in RSMA, SC is a common stream that has to be decoded by both users, but does not necessarily, the content is not necessarily intended to both users. I have here part of the message of user 1 and user 2 into SC. So in this case, there is information for both users into SC, but I could have a scenarios where only part of W1 is into SC, but I don't have WC2 here. So I only split one of the two messages. In that case, SC will carry information of only part of the information of W1 is carried into SC, but nevertheless, both users are going to have to decode them. So this is the importance of a common stream, is a stream that is decoded by both users, but not necessarily intended to both users. And NOMA has a common stream as well. This is a different from a multicast streams, where multicast, you could argue that the content is intended to both users. So another way to look at that is the following, is the difference between those different multiple access schemes is how we map messages to streams. And so I mentioned we have 3 streams, right? In contrast to MULP, we have 2 streams. NOMA, we have 2 streams. Now we have 3 streams. We still start from the same messages, W1, W2, but instead of creating 2 streams, 2 private streams here, or 1 common stream and 1 private stream, now we create 3 streams. We have 2 private streams and 1 common streams. And so when I do SDMA, essentially I don't use the common streams. I put nothing into the common stream. I map W1 into S1, W2 into S2. When I do NOMA, I don't use one of the private streams here. I map W1 into S1, and W2 entirely is mapped into the common streams. When we have orthogonal multiple access, we don't use the common stream and we don't use the private stream. We use only one private stream to deliver a message to one of the users. And if you do multicasting, well, you don't use the private stream. You take those 2 messages and you encode them directly into the common stream so that both users will decode that common stream. Right, so what is rate splitting? Well, rate splitting split those messages into 2 parts. Each part is split into 2, each message is split into 2 parts. So I have WP1 and WC1, WP2 and WC2. And so by doing this, what we have is that anything that falls into those 2 columns here, any interference that I have between those 2 columns, those 2 streams is treated as noise. Anything that falls into this right column here is fully decoded at the receiver. And so anything that falls into SC is decoded by both receivers. Anything that falls into those 2 columns is decoded by its intended users and treated as noise by the other users. And so read rate splitting, we can adjust the content of S1, S2, and SC such that depending on how we split the messages, depending on how we allocate the power to those different streams, we can actually fall down to SDMA, NORMA, OMA, or multicasting, or we can have something that is not any of those four schemes. So we end up with a more general framework where rate splitting is a superset and include SDMA, OMA, NORMA, and multicast as particular subschemes. So how do we split the user messages? So here's an example, same architecture, but based on bits. So we have W1, W2. This is essentially a stream of bits, and I have bits here, A1 to A4. Let's say I have 4 bits in my message for W1. For W2, I have 3 bits. And so because I have 4 bits, I can have maybe 16 possible messages here. And here I have 3 bits, so I have 8 possible messages. And when we split, we essentially take bits away. So we take, for instance, the first 2 bits. I decide, for instance, the first 2 bits goes into the common part. The last 2 bits goes into the private parts. For instance, in user 2, the first bit goes into the common part. The last 2 bits goes into the private parts. And when we do the combining here, we take those first 2 bits here for WC1, these bits for WC2, and we combine them together. So now I create a common streams here that has 3 bits. I create a message, a common message that has 3 bits, and then we can encode this into a common stream and so on. Similarly, WP1 will have 2 bits. I can encode this into a private streams. WP2 has 2 bits. I'm going to encode into a private streams. And so at the receiver, each receiver will decode WC, and then user 1 will try to retrieve WC1, will retrieve those first 2 bits. WC2 will decode WC and will retrieve the last bit here, B1, and then will recombine with the private parts, WP1 and WP2, to reconstruct the original message, W1 and W2. Right, so this is how it would be done at the physical layer and how the bits could be split. Now, we can do this for K users, for a general number of users, K larger than 2. So this is an example of a general framework, generalized rate splitting framework when we have 3 users. And now what we do here, we take 3 messages because we have 3 users, 1 message per user, and we split them into multiple parts. We don't split them only into 2 parts like here, 1 and 2. We split W1 into here 4 parts, 1 part here, 2 and second there, third one, and fourth one here. And each of those parts can be decoded by a subset of the users. For instance, this one will be encoded into a private stream decoded by user 1 only. This part here, the superset, the superscript here says 1, 3, so that will be decoded by user 1 and 3. So that will be encoded into a stream S1, 3 that will be decoded by user 1 and 3. 1, 2, one part that will be decoded by user 1 and 2, and 1 part that will be decoded by user 1, 2, and 3. And so at the receiver, because we have 4 split here, we're going to end up with 3 SIC. So we're going to have the receiver will first decode the common stream here that is actually to be decoded by user 1, 2, 3. Then from there, it will retrieve the part that is intended to user 1. So that's this part here. Then it will perform SIC, will decode the second stream, let's say S12, will retrieve W12. From there, will retrieve the part that is intended to user 1, right? That's this one here. And it will continue with S13, with S1, and will reconstruct here those 4 subparts of the messages and then recombine them into the original message. And we can show here again that SDMA and NORMA are subset of this general rate splitting framework. SDMA is obtained by turning off all those common streams here, all those one here are turned off, and NORMA is obtained, for instance, by keeping S1, S12, for instance, and S123, for instance. So this is explained in general in this paper, how this general framework of rate splitting can be used. And this is very powerful because if you can optimize this, you know exactly which streams contribute to your overall objective functions. Is it more the private streams? Is it more the common streams? Which common streams? And according to that, you can also prune and remove some of those streams because they don't contribute so much to the performance. So for instance, I can say, well, maybe S12, S13, and S23 do not contribute that much to the performance. So what I can do is having only one common stream, S123, and 3 private stream, S1, S2, and S3. That would be a sub-strategy of this generalized rate-splitting multiple access. So this is very powerful because you can always identify subsets that actually perform well and so would decrease the complexity. So if you're interested into more details of this rate splitting framework, I invite you to look at those papers that compare RSMA with SDMA norma. This is the general rate splitting multiple access framework that really compares with SDMA norma that introduced generalized rate splitting. We have this that shows that for 2-user scenarios, how based on a very simple 2-user rate analysis, rate splitting can unify SDMA, OMA, norma, and multicasting. We have this recent paper that look at have a critical look at next generation multiple access that look at whether norma is efficient in multi-antenna by comparing with SDMA and rate splitting in terms of degrees of freedom and identify the misconceptions and misunderstanding of multi-antenna norma. These schemes here, these papers looks at how dirty paper coding, how we can get performance beyond dirty paper coding when we have imperfect CSIT, or so-called partial CSIT. This paper here has looked at DOF also, DOF of when we have different scenarios here, when we have multi-group multicast, we have rate splitting, when we have non-orthogonal unicast and multicast transmissions that also compare with SDMA norma. And we have this paper that performs cooperative rate splitting when we have user relaying that also compares with SDMA norma. So all those papers actually compare with SDMA norma and show that rate splitting always outperforms them. And the gain depends on the specific objective function and the specific scenario. Right, so let's look at some low complexity RSMA, and I have already hinted on one of them. So one of them here is based on that. What if I turned off some of those streams and only keep one common stream that is decoded by all? And this is what we call here this one-layer rate splitting. It was actually the first and maybe simplest strategy they can use for K user that we introduce in this paper and in another paper that I will introduce in a minute. And that writes very simply as follows. We have K users, and we transmit K private stream, SK, S1 to SK, and one common stream, SC. So SC here, in this case, would be the same as this S123 here. So it's a common stream that has to be decoded by all the users, by all those K users, and will carry information that could be intended to one of the users or a subset of those users. And this is very simple because only one SIC is required, the receivers. So you have K users, but only one SIC. You don't need to do any user ordering, user grouping, which user will decode which stream with what ordering. No, all users simply decode that common stream and then decode their private streams. Multi-user linear precoding, SDMA, is a subset of this by turning off this common stream. So you always get performance that will be equal or better than SDMA. And norma here is not a subset of that architecture, of that specific one-layer RS, unless we have a 2-user. So in the 2-user case that I've shown before, then norma is a subset of this framework. But if you have more than 2 users, then norma is not necessarily a subset of that schemes. So how this works? Well, this is as follows. We have, again, we have K streams, K messages, and now we split each of those messages at most once. So, for instance, W1 goes into WC1 and WP1, WK and WCK, WPK, and so on. We combine those common parts into a common message here, And now we have k messages here at this level that are encoded independently into k streams, and we linearly precode them. And at the receiver, each receiver decode SC, and from SC will retrieve the part that actually is intended to user K. So user K will retrieve WCK here, and then will perform SIC, will retrieve WPK from SK here, and then will recombine into the original message. Again, you don't always need to split all those messages. That will really depend on your objective function and on what you want to do, and maybe the user deployment. You could have a scenarios where actually only one of those K streams or those K messages is actually split. So you could have WK goes directly into SK, W capital K into S capital K, but only user one message is actually split into a common and private part. That could happen as well. In that case, the common stream will only carry information intended to user one, but it would have to be decoded still by all the users, right? So this is actually adjustable, which bits goes into what streams and how many messages we need to split. Right, something slightly more complicated. We have now, instead of having one SIC as we have here, we allow to have two SICs. And to have two SICs, we have two types of common streams. And this is what you call a two-layer rate splitting, also called hierarchical rate splitting, that was originally introduced in the massive Mimo context in this paper. And so here we have 4 users in this example. They are split into 2 groups. We have a group 1 here, and we have a group 2 here. And here we transmit 2 types of common stream. We have a common stream SC. In this figure, SC is actually S1234. So this is actually a stream, a common stream that has to be decoded by all those 4 users. And then we have a group common stream. We have a common stream that is intended to this group 1. We have a common stream intended to this group 2. And so, for instance, we have a common stream S12 and S34. So S12 will be decoded by both user 1 and 2, S34 by user 3 and 4. And then we have the private stream S1 and S2. And so a given user 1, for instance, would have to decode S123, 4, then perform SIC, decode S12, then perform SIC, and then decode S1. And from those 3 streams, we'll reconstruct his original message. Again, MULP SDMA is a subset of this architecture. If you turn off all those common streams here, or S12, S34, and S1234, you obtain SDMA. And NOMA is not necessarily a subset of the 2-layer hierarchical rate splitting. It depends on what type of NOMA schemes we use. It could be a subset of this, but it may not be. Right. So this provides some additional performance gain over this architecture because we have essentially this set of common message. So we have actually a common message that is intended to each group G. So we have a common message here, S12, that would be for group 1, and we have another one that would be for group 2. Right, if you're interested in those low complexity rate splitting architecture, I invite you to look at this overview paper, a tutorial paper that we published a few years ago. The first paper that really looked at the sum rate optimization and showed the optimality of actually rate splitting from a DOF perspective is in this paper here. We have, and that paper relies on this architecture here, this 1-layer rate splitting. Energy efficiency has been looked at also using 1-layer rate splitting in that paper, and the optimization and the design of based on 1-layer rate splitting has been looked at in those 2 papers as well. Right, so far we looked at linearly precoded rate splitting multiple access, but we can do something else. We can, instead of encoding here those private streams into those private message into private streams, and then linearly precode them, what we could do here is to do nonlinear precoding on those private parts. And this is what we obtain here. with this architecture, this is a one-layer rate splitting architecture where this part has changed. So here, to encode the private parts into the private streams, we now use dirty paper coding. And so the reason for this is the following. We know that if we have perfect channel state information at the transmitter, DPC is capacity achieving. So that means actually if we use this architecture in a scenarios where we have perfect channel state information at the transmitter, the optimization will allocate 0 power to the common streams, and this architecture will boil down to DPC. On the other hand, if we have imperfect channel state information in the transmitter, then DPC is not capacity achieving, and we can have performance enhancement over DPC by starting allocating some non-zero power to the common stream. So we will leverage the power of DPC to manage the interference between the private streams, but we will allocate some power into the common stream in order to benefit from the multiplexing gain increase of rate splitting. So this is discussed in more detail in this paper. Right, so if you're interested in a more complex architecture based on non-linearly precoded rate splitting, I invite you to look at this paper here when we combine with DPC. This one is also DPC coded rate splitting, but for slightly more complicated scenarios where we have non-orthogonal unicast plus multicast transmission. DPC is difficult to implement in practice, so instead of using DPC, we could use some other forms of nonlinear precoding. So for instance, Tomlinson-Arashima precoding. And so in that case, here, instead of doing DPC, we could do Tomlinson-Arashima precoding to encode those private streams. And this is done in those two papers that I invite to have a look at if you're interested. Right, so how can we summarize this into one graph is the following. SDMA, on one hand, treat interference as noise. This is actually a subset of a more general class of strategy that is called one-layer rate splitting. One-layer rate splitting includes SDMA and multicasting as two subschemes. Then above this, we have two-layer hierarchical rate splitting that is more general than one-layer rate splitting. We have NORMA, on the other hand, is one particular type of multiple access that fully decodes interference. And RSMA is the general framework that actually encompasses all those different strategies into one unified methodology and framework. And so that's the power of RSMA. It can boil down to SDMA, multicasting, NORMA in some specific scenarios. It could boil down to some other schemes in other scenarios. In general, it always gives you performance enhancement, but also it can identify some other strategies. For instance, one-layer rate splitting here that also relies on SIC, but only one SIC. So it enables to find communication strategies that are not NORMA-like strategies, but that perform better than multi-user Mimo with a much lower receiver complexity because it has only one SIC, which contrasts with NORMA that can have quite many SIC. So we'll show later on that just one-layer rate splitting can actually beat SDMA and NORMA, even though it has only one SIC. So this is another benefit of this general framework, is to be able to identify how to actually make use of those common and private parts and how to make use of SIC efficiently when we have multi-user, multi-antenna communication. So let's look at degrees of freedom of rate splitting multiple access. So this is the scenarios I've looked at before of how we model the imperfect CSIT. This is our system model from RSMA. From one-layer rate splitting, we have the common streams and we have the K private streams. So let's look at the DOF as a function of alpha. So what we can show is that if we do precoding of the private stream using zero forcing beamforming, we can have some interference level here that is left. That's the same as when we do SDMA. And so this part here is the same as what we had earlier on in the talk. But additionally, now we have here the common streams. And so we can calculate what is the SINR of the common streams and the private streams. And we can calculate from this, we can calculate the degrees of freedom of the common streams and the private stream. And we can show that each common stream achieves a degrees of freedom of 1, the common stream here, SC, achieves degrees of freedom of 1 minus alpha. And each private stream, each SK, achieves a degrees of freedom of alpha. So because we have K of them, we have a sum DOF of the private stream that is equal to K alpha. And we have 1 minus alpha additionally that comes from the common streams. And so the sum of those two gives us 1 minus alpha plus K alpha. This is strictly larger than the K alpha that we had early on, right? If we remember what we had for MULP, we had here K alpha. Now we have a sum DOF that is larger than that. Because I have the presence of the common stream, I have 1 minus alpha extra. Here I have a 1 minus alpha extra. So what does that mean? If I have alpha equal to 1, if I have alpha equal to 1, this is the same as having accurate CSI from a DOF perspective. Alpha equal to 1 will give me a degrees of freedom for the common stream equal to 0. The common stream will not contribute to the DOF when I have a perfect CSIT. But if alpha is smaller than 1, then this term is non-zero and decrease the DOF compared to what I had with multi-user linear precoding. And that's the beauty of the rate splitting, is that if I have alpha that is strictly smaller than 1, essentially I have a DOF enhancements over multi-user Mimo, multi-user linear precoding. This was shown in this paper in more detail, and it was shown actually this is optimal. You can show that actually this match the information theoretic optimality that was derived in some recent other papers. Right, so we can show that the degrees of freedom optimality is when we have M larger than K, so more antennas than the number of users. In the MISO BC here, we can show that actually this is the optimal degrees of freedom, information theoretic optimal degrees of freedom, and that rate splitting achieves that. Does not only achieve the sum DOF, but we can show that it achieves the entire rate region, optimal degrees of freedom region. If you don't do rate splitting, on the other hand, you get at most a degrees of freedom of K times alpha, which is the same as what we get with rate splitting if alpha is equal to 1. So if you have perfect CSIT, the DOF is the same. But if alpha is smaller than 1, so if you strictly have imperfect CSIT, then the no rate splitting strategy, so MULP kind of strategies, achieves a DOF that is strictly smaller than the rate splitting. And this is an example of the degrees of freedom region. So you have the degrees of freedom region of degrees of freedom of user 1, degrees of freedom of user 2. And you see the blue one is a degrees of freedom region of achieved by rate splitting, which is larger than the green one that is obtained by MULP, and larger than the dashed one that is obtained by TDMA and NORMA, would be the dashed one. And so you have a gain here, and you have two corner points, and those two corner points depends on how you make use of the common stream. Do you make use of it to carry information for user 1, or do you make use of it to carry information for user 2? So the baseline, you see that we can enlarge these degrees of freedom region. That means actually we can have a faster increase of the rate at high SNR compared to MULP and NORMA. And this is the optimality of the degrees of freedom region when we have imperfect CSIT was shown in this paper. Right, so I had this figure here early on where I was saying, well, if you have two schemes that actually both of them are designed for two antennas and two users, the blue one and the red one, for instance. I was saying early on, well, what is the best one is the one that has a higher DOF. Because at least you know that as the SNI increase, that schemes will actually have a sum rate or the achievable rate that increase faster with the SNR. And this is really what we see here. We have the rate splitting in red for both those two setups here have a DOF that is actually larger than what is achieved by multi-user linear precoding. And the gain can be quite significant here. In this two-user case, we have 50% enhancement in terms of DOF compared to what MULP can provide. So this DOF enhancement leads to a slope enhancement, which translates into a rate enhancement. And you cannot achieve a slope that is better than what is achieved by those red curves that is achieved by rate splitting. So what is achieved in the blue one by multi-user linear precoding is strictly inferior to what is achieved by rate splitting. Right, so now let's look at how these degrees of freedom changes as a function of the number of SIC layers. So to do that, I will look at two different metrics. The first one is the sum DOF, and the second one is a max min fair DOF. So the sum DOF is a measure of how the sum rate scales with the SNR. So we're looking at the pre-log factor of the sum rate. So the sum rate is a sum of the rate. I'm looking at the pre-log factor of the SNR, of the pre-log factor of the sum rate. And this is what we have been looking at so far, right? That was the sum DOF. A max min DOF is looking at how the minimum rate among those K users will scale with the SNR. So I'm looking at the pre-log factor of the minimum rate among those K users. So I'm looking at two completely different metrics. The sum DOF relates to the sum rate, which is trying to put as much throughput into the network, but it's not necessarily a fair metric. The max min fair DOF does not necessarily try to maximize the throughput in the system, but try to be fair among all the users in the sense they try to make sure that the weaker users maximize the rate of the weakest users as much as possible. Right, so two different metrics. One favor a bit more fairness, the other one favor really maximum rate. And I have two figures here, perfect CSIT and imperfect CSIT. And for each figure, I have the sum multiplexing gain of sum DOF and the max min fair DOF. So the blue one will be sum DOF, the red one the max min fair DOF. And what we see is the following. We have number of SIC layers. So as you increase this, as you go from the left to the right, you increase the complexity. As you go from the top here to the bottom, you decrease the multiplexing gain. So in other words, you decrease the performance. So what you want to do is to be in this corner here. High performance, low complexity. And you don't want to be in the bottom here, low performance and high complexity, right? If you do MULP, MULP works really well in terms of sum DOF with perfect CSIT. In terms of max min DOF, unfortunately here in this setup where we have 4 users, 6 users and 4 transmit antennas, and we really want to deliver information to those 6 users, MULP cannot cope with the multi-user interference. So it's DOF, MMF DOF drops. MISO norma, and here we have 2 types of MISO norma, 1 groups and 3 groups. And we see that they have completely different performance. This one is okay in terms of some multiplexing gain. This one is pretty bad in terms of some multiplexing gain. This one has a low max min fair multiplexing gain, but this one has a better max min fair multiplexing gain. And our rate splitting, 1 layer rate splitting is here. So for both some multiplexing gain and max min fair multiplexing gain, it achieves higher performance. And it does this with only 1 SIC, which is this sharp contrast with any of those NORMA schemes that needs either the same number of SIC but perform much lower in terms of DOF, or actually have much higher complexity at the receiver and also perform worse in terms of DOF. So you really see from this figure that the NORMA schemes is quite inefficient in making use of the multi-antenna dimensions and the SIC architectures. You can have DOF that is even worse than having just MULP. You see that actually the blue curve here, MULP performs better than here and better than there, even though MULP has no SIC, right? So that really means that the SIC in NORMA are badly exploited or very inefficiently exploited. The one SIC in rate splitting gives you a performance enhancement over MIMO or MULP. At least it has at least the same degrees of freedom or better. If we move to imperfect CSIT, the gap is increasing, and so we see here that the rate splitting is actually strictly higher than any other schemes. So the main results here is that one-layer rate splitting achieves larger sum and MMF multiplexing gain than MULP and NOMA, and it does this with one single layer of SIC. If you are interested for more details, you can look into that reference. Right, so now let's look at sum DOF. So I looked at both sum DOF and max mean fair DOF here. So now let's focus on the blue one here. So sum DOF again is the pre-log factor of the sum rate. And I'm looking at this for perfect CSIT and imperfect CSIT, but I'm looking at this as a function of the number of users, not as a function of the number of SIC. And what we see is that we have perfect CSIT and we look at sum multiplexing gain, actually MULP and one-layer rate splitting are equally good. And we know this already. If we have perfect CSIT, we have sum DOF, MULP is achieved the optimal multiplexing gain. So it's good enough. No need to do rate splitting in that specific scenario. If you do NOMA, on the other hand, you increase the receiver complexity, but you get even worse performance. The sum multiplexing gains drops. So that's a major problem. If you go to imperfect CSIT, this is where we see gain of rate splitting here. Rate splitting strictly outperforms MULP, but also outperforms NOMA, whatever the number of users. Right, so sum DOF of one-layer rate splitting is always larger than or equal to any other baselines for the different number of users. Right, so what if we want to look at max mean fair DOF versus the number of users? So again, I'm looking at how this minimum rate scales with DSNR. So I'm looking at the pre-log factor here of the minimum rate. And this is really important when we look at how many users we can serve in a massive kind of access scenario. So as the number of users increase and we want to be able to serve more and more users, we want to make sure that all those users are served with a non-zero rate. And so this is what this matrix will tell us here. You see that if you have 6 antennas and you have a number of users that is smaller than 6, then MULP is quite nice. It's actually achieved the best performance. Once the number of users is larger than 6, then MULP drops very quickly. It's actually once it's strictly larger than 6, then it's equal to 0. So you have an MMF DOF that is equal to 0 because you cannot handle the multi-user interference. Right, if you do NOMA, well, if you have something that is larger than 6, you have, depending on the NOMA schemes, the yellow one here with 2 users per group is not very good. If you do the NOMA with only 1 group, so you have K users in 1 group, then it's actually slightly better. And the blue one is rate splitting. So what you see here is that at this point here, NOMA and with 2 users per group and MULP cannot serve more than 8 users. Then max mean fair multiplexing gain is equal to 0. If you look at NOMA with 1 group and K user in that group, and if you want to achieve a max mean fair DOF of 0.1, then NOMA with 1 group can serve 10 users. And to do that, you would need, if you have 10 users in 1 group, you would need to have 9 SIC. On the other hand, you can do better than that. You can do rate splitting, and rate splitting is here, would actually achieve the same max mean fair DOF of 0.1, but would do this, could serve 15 users, right? To achieve the same max mean fair DOF, it would serve a larger number of users, it could serve a larger number of users, and it would do this with only 1 SIC. So you see here again how you can increase the number of users to be served. You can serve more users. Instead of serving only 10 users, you can serve 15 users. And you do this with only 1 SIC instead of 9 SIC as it would have been done with NOMA. right? And the same observation is obtained when we have imperfect CSIT, the gap is widening. So again, one layer rate splitting here is significantly more efficient than NORMA, since rate splitting with only one SIC layer can support a larger number of users than NORMA that would require many SIC layers. More detail again in this paper. Right, so if you're interested, I invite you to have a look at this literature here. The sum DOF optimality was shown in this paper in TCOM 2016. The optimality of the whole DOF region is shown in those two papers. The symmetric DOF, which is something I've not talked much about, this is a different way of defining degrees of freedom, is when we have partial CSIT is shown in that paper, where we show again superiority over MULP. If you have another setup where we have multi-group, multicast, we can find also DOF in those two papers with perfect CSIT here and imperfect CSIT there. And then if you want to compare the DOF, sum DOF, max mean fair DOF of all those multiple access schemes, everything is summarized into this recent paper. Right, so now that we have a DOF gain, how does that translate into a rate gain? So here we look at the rate enhancement of RSMA, and we investigate this rate as a function of the user channel alignment or orthogonality and the channel strength disparity. So to do that, let's consider two channel vectors. The first one is given like this, and the second one has two parameters. The theta, as we increase theta, essentially we increase the angle between H1 and H2. And as we decrease gamma, if gamma is equal to 1, we have the same channel strength for both channels, for both users. If gamma is smaller than 1, then we increase the channel strength disparity between those two users. And as a function of gamma and theta, we want to see how the rate region achieved by those different multiple access changes. And so this is what we have in those four subfigures here. We have gamma equal to 1, so there is no channel strength disparity, but we changed theta. So as we go from A to D, we increase theta, we increase the angle between the two channels. And we have four curves for each of those subfigures. Yellow one is NORMA, green one is MULP, so this is SDMA, red one is rate splitting, and the blue one is the capacity region. This is achieved by DPC. We have here perfect CSIT. So we cannot get better than the blue curves. That's the capacity region. No way we can get better than that. But what we see is that the rate splitting comes quite close to the capacity region, especially in scenarios where we have the angle between the channels is not very large, right? And it outperforms always MULP and NORMA. If the angle is very large, like here, then it's sufficient to use MULP, right? Because the channels are orthogonal, so we know that then multi-user linear precoding is sufficient. Right, so what if we have a disparity of channel strength? We keep perfect CSIT, but we have a disparity of channel strength. So now we have gamma is 0.3, so there is 10 dB gap between user 1 and user 2 channels. And now we see with the same theta, we see the shape has changed. NORMA was the worst one compared to MULP. Now NORMA is better than MULP, but rate splitting is always equal or better. As we increase the angle, well, you see that the NORMA does not enhance better. It does not get any better. MULP gets better as we increase the angle between the two channels, but rate splitting always outperforms them, and so on as we increase the angle between the two channels. But this is discussed in detail in this paper. Right, so now because rate splitting, multiple access is a general framework that enables to a general framework that is a superset of SDMA, NORMA, and OMA. We can use this to identify in what regime splitting boils down to SDMA, NORMA, and OMA. And we do this as a function of two parameters here. That's a function of the angle between the two channels. So if rho is equal to 0, it means that the two channels are aligned with each other. If rho is equal to 1, it means that the two channels are orthogonal to each other. And as a function of the disparity of channel strength. And we do this in terms of, we look at weighted sum rates. And we have perfect CSIT. So this is done in this paper. And we see how actually rate splitting boils down to existing schemes as a function of those two parameters, rho and channel strength. And so this is if you have U1 and U2 are equal to 1. So essentially you have a sum rate scenario. You see that if you have a large angle, so if you have rho is large, so you have quite orthogonal channels, then rate splitting boils down to SDMA. If you have, on the other hand, a disparity of channel strength, or if you have a low angle between, a small angle between the channels, then rate splitting boils down to OMA. And in between, you actually perform really rate splitting where you have to split the messages. NORMA is here out of the picture. It actually would be outperformed by any of those. So it would be, there would be no need to do NORMA here. If you put more emphasis on user 1, you get this kind of behavior. Again, NORMA disappears of the pictures. Same kind of behavior as here. If you have very orthogonal channels, you do SDMA. If you have really disparity of channel strength, you do OMA. On the other hand, if you have the weaker user, you put more emphasis on the weaker user. So the weight of the weaker user, user 2, is larger than the weight of user 1. Then in that case, you still do SDMA if you have large angle between the two users, but then NORMA starts playing a role here if you have really large disparity of channel strength. And in between, you perform rate splitting, multiple access. Right? So this is really shows you how rate splitting boils down to the different schemes, depending on the angle and the disparity of channel strengths. All those details are here. Right, so now what if we increase the number of users? Instead of having 2 users, 2 transmit antennas we have here, what if now we have 10 users in this system, but we have 2 transmit antennas? This is really something that is advertised in the NORMA literature, that the NORMA can serve a larger number of users. And I've already mentioned, based on the DOF analysis, that actually it can support potentially a larger number of users than, for instance, MULP, right? So NORMA here, this NORMA here can support more users, 10 users, whilst MULP cannot. So that's not bad, but it's still pretty inefficient because you could do much better than that with a fewer number of SIC. And this is what we see here in this figure as well. If I want to support 10 users, so I want to maintain quality of service to the 10 users, but I have only 2 transmit antennas, then if I do NORMA, I do a bit better than MULP. But I can do much better than that. I can do 1-layer rate splitting, which gives me a significant performance enhancement over NORMA and MULP. So NORMA is in yellow and MULP in green. I can have significant performance enhancement, but also with a much lower complexity. Rate splitting has only 1 SIC. NORMA here in yellow has 9 SIC. So the green one, MULP, has 0 SIC. That's the simplest receiver. So to go from green to yellow, you need to go from 0 SIC to 9 SIC. You need to increase significantly the receiver complexity to get a relatively small performance enhancement. You can do much better than that. You can have only 1 SIC and having rate splitting providing a significant performance enhancement. So again, that shows you how this rate splitting that does not try to treat interference as noise or doesn't try to force to fully decode interference, but try to partially decode and partially treat interference as noise through the presence of the common streams, can come up with actually very powerful strategies that gives higher rate, higher quality of service, higher robustness to CSIT imperfections, and a lower complexity as well. Right, that translates into rate region enhancement as well. So this is imperfect CSIT setting. I have the ergodic rate of user 1, ergodic rate of user 2. This is fully optimized, and Lena will talk about this in the next part. This is the rate region. And we see that as the SNR increases, the gap between rate splitting techniques and no rate splitting, despite the fact it's fully optimized, this gap is increasing. And this comes from the multiplexing gain benefits of rate splitting over no rate splitting. So consequently, rate splitting achieves a larger rate region. This is shown in detail in this paper. Right, continuing with rate enhancement with imperfect CSIT, we show here in this figure that you can actually have one layer rate splitting, which is in red, outperforms norma in yellow and MULP in green. We have seen this already before, but interestingly, it can outperform DPC as well. So DPC is in blue, and we know that DPC is capacity achieving when we have perfect CSIT, but we don't know what is the capacity achieving strategy when we have imperfect CSIT. So according to the current method, if you know there is the best strategy in imperfect CSIT, you would use DPC if it's the best strategy in the perfect CSIT, you would use that strategy when you have imperfect CSIT. And this is the best you would think you could do. So you would use DPC in the imperfect CSIT setting. What we show here is that you can do better than that. If you do one layer rate splitting that does not rely on nonlinear precoding, that just relies on linear precoding and just one SIC, this strategy would outperform DPC. And you can do even better than that if you combine DPC and rate splitting into this DPC coded rate splitting that provides additional rate region enhancement over one layer rate splitting, over the linearly precoded rate splitting. So this purple one, the largest one, is obtained by the strategy that I showed you earlier, that is obtained by this one. So where the encoding of the private parts is done using dirty paper coding. Right, so this shows you that you can have very powerful schemes based on rate splitting that would outperform the conventional non-rate splitting schemes like SDMA, MULP, Mimo, NORMA, and even dirty paper coding. This is shown in that paper. Right, so this was in terms of rate region. We can also look at robust max-min fairness. So here we're looking at maximizing the minimum rate among all K users. And we have imperfect CSIT, and this is based on optimization, again, that Lina will talk about. And what is the main message here is that you see that if you don't do rate splitting, at some point, you actually have your rate saturates at high SNR. And this is because the SINR is dominated by the interference, which leads to a saturation of the SINR and leads to actually a saturation of the rates. On the other hand, if you do rate splitting, because of the presence of the common streams, actually the rate never saturates. And so as the SNI increase, actually we can achieve a non-vanishing rate. So rate splitting saturates due to the multi-user interference that is coming from the imperfect CSIT. Rate splitting, on the other hand, avoids the saturation and provides gains across a wide range of SNR, from the low SNR regime to the high SNR regime. And this is shown in that paper. Right, so to conclude, here, rate splitting multiple access, multiplex user in the spatial domain and the power domain. So you use the multiple antennas, but you also superpose them in the power domain using the private and the common streams, using linearly precoded rate splitting techniques and SIC at the receiver. And so what's the property is to partially decode interference and partially treat interference as noise. So that's completely different from MULP that is used throughout 4G and 5G, which relies exclusively on treating interference as noise. It's very different from NORMA that forces itself to always fully decode interference. So one user has to decode the message of other user, has to fully decode the message of other users. Here we partially decode, we partially treat interference as noise, and we adjust this part, how much we want to decode, how much we want to treat as noise. And thanks to that, we can bridge the extreme of NORMA and SDMA, and we can obtain a more powerful and general framework. So the advantage that we have any existing multiple access schemes like ORMA, SDMA, and NORMA are just special cases of RSMA. The RSMA rate is always larger or equal to the rate of SDMA and NORMA. We know it's optimal from a degrees of freedom perspective in both perfect and imperfect CSIT. It copes with any user deployment, whether we have a diversity of channel strengths or diversity of channel directions, any CSIT inaccuracy, and any network load, whether the network is overloaded or underloaded, whether we have more users than antenna or fewer users than antenna. And actually, it can lead to strategies like the one-layer rate splitting that has lower computation complexity than NORMA for both the transmitter side and the receiver, right? And I've shown you this quite a bit, that you can have with one SIC only, you can have much higher performance than NORMA that would need to have multiple SICs and potentially an optimization over multiple groups. The drawback is that instead of transmitting K streams to K users, we now transmit, for instance, with one-layer rate splitting, we transmit K plus one stream. So there is a slightly higher encoding complexity because we have at least one more streams to transmit. Right, so with this, I finished this first part. And now Lina will take over for the second part, and we'll talk about precoder optimization and physical layer design, and then numerous applications of this rate splitting framework in many different scenarios. And we'll then conclude. Thank you for your attention.